Hello, and welcome to your Week 7 lecture video. This week we're going to look at IPv4 addressing and subnetting, which are very, very important concepts. And we're going to come back and go over lots of subnetting again and again and again throughout the rest of the course in the lectures, just to give you a lot of practice, because you are going to need IPv4 subnetting for your practical test. So we're going to look at all of these things. The structure of an IPv4 address, the different types of addresses you get, private, public, reserved addresses, unicast, multicast, broadcast, what subnetting is, so it's actually breaking down your network into smaller networks to improve performance and for security reasons and for a couple other reasons too. And then we're going to actually look at subnetting an IPv4 address. When we get into that portion of the slides, I'm going to kind of divert from using the slides, and I'm going to do my own thing because I'm used to teaching subnetting old school on a board with a marker, because that's how I learned. So IPv4 addresses, we talked about a little bit already, right? They're 32-bit addresses. And they're actually divided into a host and network portion. You can't read an IPv4 address without its subnet mask. The subnet mask is the thing that tells you what portion of the address represents the network and what portion of the address represents hosts on that network. For all devices on the same network or subnet, the network portion of the address is the same, but the host portion must be unique, because every device needs a unique address. Hopefully that makes sense. So we see this stuff in decimal, right? Because we're people. We think in decimal numbers and hexadecimal numbers, and even that's a stretch, but we don't think in binary. But computers think in binary. That's what computers do, right? So they go through a process known as ANDing. They take the IP address and the subnet mask, and they perform a operation binary ANDing on them to determine which portion of the address represents the network and which portion is the host. The rule is, if it's a 1 in the subnet mask, it's a network bit. If it's a 0 in the subnet mask, it's a host bit. So in this example on the screen here, we see our subnet mask is 255.255.255.0. So that means the first 3 octets are all 1s, which means the network portion is the first 3 octets, which hopefully makes sense. So for every device on this subnet, these first 3 octets would have to be the same. It's an important thing. You can also look at this in terms of a prefix length, which is a little more like how we do with IPv6. It's the CIDR notation, or slash notation, whatever you want to refer to it as. All this is a representation of this. You just usually see the IP address with a slash and its prefix length, and you know based on that what the subnet mask is. And in fact, looking at that prefix length and determining what the subnet mask is an important skill that we're going to go over in our subnetting demonstration, or I'm going to go over in my subnetting demonstration with you, and you're going to learn. That's the we part. And you're going to need to do that for your practical test. It's an important thing. I've said it's an important thing a few times. I just keep coming back to that. I'm not sure why today. So computers do this in binary. They AND them. We're not people, right? Or we're not computers. We're people. We are people. We're not people. So we look at that mask, and we can tell what portion is the network and what portion is the host. Now within each type of network, regardless of whether it's a public or private IPv4 network, within each addressing space, there's 3 different types of addresses. The network address And the broadcast address, I skipped the one in the middle, I'll come back there and you'll see why. The network address and the broadcast address cannot be assigned to devices. And they're unique addresses. The network address, in the network address, the host portion is all 0. So it's commonly referred to as the all zeros. In the broadcast address, the host portion is all 1s. So it's commonly referred to as the all 1s address, or the broadcast address. The network address uniquely represents that network for things like routing. The broadcast is used for any packets that broadcast. Anything in between that, though, one IP more than the network ID to one IP less than the broadcast ID, is an assignable device that you can use for any, or assignable device, an assignable address that you can use for any device in your network, in your subnet. So I usually refer to this as our range of assignable IPs, assignable range. You'll see when we do some subnetting to kind of tie this all together. Now, in addition to that, we've got 3 different types of addresses: unicast, broadcast, and multicast. Or I guess not really addresses. I mean, there's unique addresses for these, but transmissions. So unicast is simply one packet from one source to one destination. One-to-one, uni, right? So we've got an example here. We've got a source of 172.16.4.1. We're sending it to a destination of 172.16.4.253, this printer over here. That's going to be a unicast packet, right? Because we know the destination right away. Broadcast packets are sent to every single device on the network, to all the possible hosts, except for yourself. They actually go to a special destination IP, and that's 255.255.255.255. That goes to all the hosts on the subnet. So they're broadcast. Broadcast packets degrade the performance of your network. And there's a lot of protocols that do this. They don't exist in IPv6, but they do in IPv4. And this is one of the reasons we subnet, is to reduce our broadcast domain to improve performance. Now, multicast packets are sent to a multicast address group. These are from one source to more than one destination. These can be used for things like routing, protocol updates. EIGRP and OSPF both use multicast packets to send routing updates. Other things use them too. So, in addition to broadcast, multicast, and unicast addresses, and host and broadcast and network IDs for IPs, we also have some different types of addresses. We have private IPs and public IPs. Private IPs are defined in RFC 1918, and these are globally routed. It says globally routed between service providers. They're not routable on the internet. They're commonly used internally. Oh, public IPv4 addresses. Sorry. So the public IPv4 addresses are globally routed on the internet. Your private IP addresses are not. They're not routable on the internet. They're used very commonly internally in organizations. They're not globally routable. And you've seen these. You just didn't know what you were looking at. There's 3 different types. There used to be a class system that we don't use anymore. So they did a class A, a class B, and a class C. One for each class in a private range. And the largest one is a /8, and that's 10.0.0.0/8. And you can subnet that up and divide it up as much as you want. The next down, if you subnet in accordance with RFC 1918, is 172.16.0.0/12, which under the class system was a /16, but because this is for internal use, they said, we'll make it a /12. And then the next down in your class C is a 192.168.0.0/16, and everybody's seen this one at home, right? If you've accessed your router at home, it's probably one of 3 IP addresses to get in there. It's 192.168.0.1, or 192.168.1.1, or 192.168.2.1. Could be something outside of these, but it's probably one of those, because they're the most common ones. So you can use these internally and divide them up wherever you like, and subnet them however you like to meet your internal addressing purposes, but they're not routable on the internet. Only a public IPv4 address will get you on the internet. Well, that's kind of weird for a second, isn't it? If you've got private IP addresses at home, private IPv4 addresses, you're able to get on the internet. How does that work? With NAT. NAT is Network Address Translation, and that takes your private IP address and it maps it to a public IPv4 address, which gets you out on the internet. And then your router is the one that does this translation, translates the packets back again. So this is usually enabled on your edge router that's connecting you to the internet. It can translate IP addresses in a couple different ways. It can do a pool of IP addresses internally to a single address externally, which is how your home internet works. It could do a pool of internal addresses to a smaller pool of external addresses, or it could even do one-to-one translation for a single IP address internally to a single IP address externally. Why would you want that? I'll give you a scenario where you might want that. With servers, right? One-to-one. You could have multiples of these. Multiple one-to-one static NAT mappings. So NAT's a super useful thing. We use it on the internet all the time. Now, when we looked at IP addresses previously, we looked at IPv4 and IPv6 very briefly. We mentioned IPv4 is out of addresses, right? We ran out. And part of the reason we ran out are things like this here. The loopback address is like one of the most wasteful things we did, because 172.0.0.1, you know that is your local host, right? That always maps to your loopback on any device, whether it's Windows, Linux, Mac OS, Cisco, iOS, doesn't matter, that's your loopback. Technically, any of the addresses in this range, though, would work. We threw away that whole pool of addresses for just one use. That's pretty wasteful. You may also see these addresses, 169.254.something.something. Those are APIPA addresses, automatic private IP addressing. You get one of these when you've either tried to assign a static IP on a device and it conflicts with another one on the network, or you've tried to pull a DHCP address and it failed for whatever reason. Your DHCP request didn't go through. So your Windows client will assign itself an APIPA address, which doesn't get you very far. I mentioned class A, B, and C. Here's the other classes as well. This was done in 1981 in RFC 790. It allocated the IPv4 addresses into these 5 classes. Class A was ranging from first octet beginning with 0 to 127. That's how you tell. You look at the octet. Class B was a 128 to 191. Class C was 192 to 223. Class D was 224 to 239, and Class E was used for 240 to 255. It was very, very wasteful. And that's why we don't do this anymore. We use the classless addressing that completely ignores the rules of the classes. Class D and E were reserved for special purposes like multicasting. Anything that's a multicast packet is going to have something in Class D or multicast protocol. Class E was for experimental purposes, developing new IP technologies. You'd be using something like that. And then A, B, and C, you would get one of those based on the size of your organization, and then you would divide it up accordingly. But it was extremely wasteful, and we generally ignore the classical addressing now. Now, when it comes to IP addresses, where do you go if you want to get a public address? Well, you can not go to these places anymore, but you could go to the IANA and any of the regional registrars, ARIN in North America. The rest are on the slide. I'm not going to read them all to you. They're responsible for address or assigning and allocating addresses. So the IANA allocates these 5 regional registrars, and in turn, those registrars assign these to ISPs or small businesses who require public address space. Now, as you know, we're out of public IPv4 addresses globally, so that means if you go to one of these organizations, you cannot get a public IPv4 address, but you can totally get a public IPv6 address from them, or you should be able to. And does that mean that you're out of luck if you want a public IPv4 address? Absolutely not. There's a lot of people out there that are trying to offload these addresses. And I realize I said people. I meant organizations. So we use subnetting, which is what we're sort of leading into, to divide your network, to segment your network down, for many reasons, right? One of those is reducing your broadcast domain. Why would you want to do that? Well, anything that uses a broadcast or multicast packet, think like ARP or DHCP, right? That packet is received by every single device except for the one that sent it. And when it hits a switch, it's sent out every single interface except for the one that it's received on. The only place where broadcasts stop are at a router. Routers don't propagate these. And every single router interface that connects to a broadcast domain. Broadcasts are only propagated within that. So you can look at your router and you can divide up your broadcast domain accordingly. Unless you've got VLANs, which is something you're going to learn later. Now, the problem with broadcast domains is if they're very large, your network performance is going to be really quite horrible. Because all of these protocols, like ARP and DHCP, right, will send broadcast packets when they're in use. So the solution here is to reduce the size of the network. Subdivide your network. Create subnets. And this creates smaller broadcast domains and improves your network's performance. So here's an example here. They've taken this network here. They had 400 users on a single network. That's way too many. So they divided it into 2. They put one over here. They put one over here. 200 users here. 200 users here. And they subdivided their network. Why they went from a /16 to a /24, not too sure, but that's what they did. So you subnet to reduce the overall traffic and improve your performance. You could even do this to implement security policies between your subnets. So you tend to subnet things based on their location, based on their group or their function, like your different departments in your organization tend to overlap with things, and maybe even based on your device types. You may have subnets for servers. You may have subnets for printers if you've got a common printer pool and stuff like that. So when you design your network, this is one of the things you have to take into consideration is how you're going to allocate your addresses. It improves your network performance. It allows you to improve your security. It doesn't improve your security out of the box, right? But it allows you to improve your security. It allows you to implement policies that target certain subnets and allow or prevent access based on, well, IP address ranges. And it also reduces your broadcast domain. So that's where you get that network improvement. It's a good thing. Now, how do we subnet an IPv4 address? This is where I'm going to divert from the slides. All right, so I've got my worksheet set up and ready to go. I've got some rules on the left that I'm going to make or on the right, sorry, that I'm going to make a bit bigger so we can see how things are. Now, a few weeks ago we looked at converting binary to decimal IPs, right? This is why for subnetting. I have your my binary powers of 2 down here. Again, don't try to memorize them. Memorize some benchmarks and work your way up and down, right? So 2 to the 10 is easy to remember. It's 1024. If you know that, then 2 to the 9 is half that, which is 512, and 2 to the 11 is double that, which is 2048. And 2 to the 20, I think I showed you the trick for that. 10, 4, skip 1, 5, skip 1, 6, backfill 7 and 8. It's 1,048,576. Now that you've seen that, you're going to know what that number is, right? We've got some subnetting rules that we're gonna work with in a second, but let's walk you through the process a couple times. I'm actually not going to do I'm going to do a 10 first. So 10.0.0.0/8. We need to extract the subnet mask out of this first. That's our first step. Identify the mask. It's a /8, so we know our mask is 255.0.0.0. That's important because it tells you what portion of the network address, or what portion of the address, sorry, represents the network, and what portion represents the hosts on the network. In subnetting, you can't mess with these bits. They're already reserved. But we're going to take these zeros and we're going to mess with them. We're going to turn some of these host bits into network bits based on our requirements. And I'm going to start off really easy. I'm going to do 2 subnets. So we've got our subnet mask. That's step 1. Done. Step 2. 2 to the power of n. How many is the formula you're going to use? How many bits are you going to borrow to get this number right here, the number of subnets you need, without going under? Going over is okay, but you want to keep this as tight as possible. You want to hit it exactly if possible, or go over ever so slightly. In this case, it's going to be 1, right? 2 to the power of 1 gives us 2. So we take that first host bit. I'm just writing these out as zeros because they're 8 zeros. I don't want to confuse anything, and I'm writing that out as 255 again because that's 8 ones. And again, we think in decimal. I'm only looking at this octet binary. We take that first host bit, or 0, we turn it into a network bit, a 1. And we convert that back up into our new mask. So our new subnet mask is going to be 255.128.0.0, which could be represented as a /9, right? The IP /9. Now our increment is an important thing that's going to become useful for step 5, is the value of the last bit we borrowed in the new subnet mask. In this case, it's going to be 128, right? That bit value right there. It's not always going to be the same as this number here, but in this case it is. Now we have all the information we need here to assign our addresses and fill out our table. Starting with subnet 0, the network ID of subnet 0 is always going to be your initial reservation here, what you started with. So that's 10.0.0.0. We're incrementing by 128. We're incrementing in the second octet because that's where we borrowed that bit. So our network ID here is going to be 10.128.0.0. And it's always useful to increment one more time, even if it doesn't exist. You'll see why in a second. So if we increment by 128 again, we're going to get 10.256.0.0. That's obviously doesn't exist, right? You can't have more than 255 in an octet. But we're going to leave it there anyway, so we can lay out our broadcasts. So we have our network IDs. The broadcast IP for each subnet is going to be one IP address less than the next network ID in sequence. So our broadcast for subnet 0 is going to be 10.127.255.255. And our broadcast for subnet 1 is going to be 10.255.255.255. Looks pretty easy so far, right? Now that we have our network ID and our broadcast IP, we just increment by 1 and decrement by 1, and we have our first and last usable IPs, which is usually referred to as your assignable range. So in this case, we're going to have 10.0.0.1 to 10.127.255.254. This one's going to be 10.128, whoops, .0.1 to 10.255.255.254. And we're done. We're done. It's not bad. Let's try another one. I'm going to give you a second to pause and write it down, and then we'll continue. Right. So, I'm going to erase most of this. And now we're going to do something from that private class B range. So 172.16.0.0. I'm going to treat it as a /16, even though technically if I follow the RFC 1918, I could treat this as a /12, right? But I'm going to treat it as a /16, which tends to be how you see this implemented. All of the rest of that changes. But I'm going to do the exact same thing, 2 subnets. And you're going to see the math is actually exactly the same, it's just in a different octet. So 172.16.0.0. What is our first step? We need the subnet mask, right? Which in this case is 255.255.0.0. How many bits do we need to borrow? Exact same math as we just did, right? 2 to the power of 1 gives us 2. We need to borrow 1 bit. Oops, 1, 2, 3, 4. 1, 2, 3, 4. So we borrow our bits. We convert that back into decimal. And we get our new subnet mask. Step 3. The increment, also useful for step 4, is going to be 128, right? It's this bit value here, which is 128. And now we have, again, all our information we need to fill in this table. So our network ID for subnet 0, that's going to be 172.16.0.0. This one's going to be 172.16.128.0, right? We're incrementing by 128. We're incrementing to the 3rd octet. That's where that's going to go. And if we increment one more time, we get 256.0. Now for our broadcasts, we have 172.16.127.255, right? One less than our network ID. 172.16.255.255. This one's going to be 172.16.0.1 to 172.16.127. Yeah, 127.254. Looked funny for a second, but no, it's correct. 127 threw me off because where we're incrementing. This one here, that's going to be 172.16.120. Yeah, 129. Oops. 129. 128.1. Must be getting tired because I'm making some silly mistakes. 172.16.255.254. And we're done. We're done. Now when you're doing this, you could increment here and here, right? All across the board. I don't recommend doing that. Increment here, use that to backtrack and figure out your broadcasts and use that to fill in your range. Because if you mess up in your increment somewhere, all your math is going to be wrong and your IP addresses from wherever you mess up onwards, oh, they're just going to be wrong. It's a lot easier to catch if you just do it in the network ID portion, because one of these IPs won't work out to be what it should be, and you should see the error, hopefully. So, let's try a /24 then. Gonna get rid of all this stuff. We'll do some more that aren't two subnets. Do 192.168.0.0/24. Literally all the same math, though. So we need our subnet mask. It's a /24. That means the first 24 bits represent the network, which is 255.255.255.0. How many bits are we going to borrow? Again, to get two subnets, we're going to borrow 1 bit. So that looks like this, right? Our new mask is going to be 255.255.255.128, and our increment, again, is going to be 128. And now we have everything we need to fill this in. If you can do this, like this is 50% of your marks on your final, on your practical test. Our network ID for subnet 0 is always the initial reservation. For subnet 1, we're incrementing by 128. We're incrementing in the 4th octet. So it's going to be .128, right? And if we do it one more time, we get an invalid IP, but it helps us for figuring out our broadcast. So now we can figure out broadcast IPs, which are going to be one less than each network ID in sequence. This one's going to be 192.168.0.127. And this one's going to be 192.168.0.255, which gives us 0.1, 2, 126, and I'm just going to copy paste because I can do that. Well, that worked out beautifully. This, of course, is going to be 129 to 254. And we're done. I know you're probably thinking to yourselves, well, that's not too difficult, right? That's pretty easy. Don't get overconfident. Practice a lot. I know I've gone through one of each, right? Normally at this point, I think I'll do another one of each, but normally at this point I'd go through one with you and I would prompt you for the answers. I guess the only way you could do that in an asynchronous format is if you see me lay it out before I do anything, right? I do my addressing space up here and my number of subnets. Pause the video, try to work it out, and then unpause and see if you got the right answer. Follow along and see if your math checks out. It's a good test. Anyway, gotta get rid of all that. And we're gonna do something a little harder. We're gonna do 12 subnets. And I'm gonna start with a 10. So the math's gonna be a bit different, but it's not all that much different than what we've already been doing, right? It's just different numbers. We have our initial reservation. We have our number of subnets. We need our subnet mask. That's going to be 255.0.0.0, right? Because it's a /8. Now, how many bits do we need to borrow to get 12 without going under? Going over is okay. 2 to the power of 3 only gives us 8. That's not enough to fulfill our requirement. We're going to have 3 networks that don't have addresses. We need to borrow 4 bits. That's going to give us 4 extras. We're going to get 16. That's okay. We got room for expansion. So we take those first 4 bits now. Turn them into network bits. We turn those zeros into ones. Convert that back. We're going to get 240. Right, 255.240.0.0, and you're probably thinking to yourself, sir, you did that really quick. How did you get that? You just add the bit values, right? 128 plus 64 plus 32 plus 16 gives you 240. Our increment in this case is going to be that bit value right there, 16. See, we got an example where those don't match. The rest of it is exactly the same. You want the network ID of subnet 0? That's going to be your initial reservation, 10.0.0.0. We're incrementing by 16 this time. We're incrementing in the second octet, so this is going to be 10.16.0.0. This one would be 10.32.0.0, which actually totally exists in this case, right? Because we have 16 subnets. And you could keep going. I'm not going to keep going, in the interest of a shorter video. The broadcast IPs, same deal, 10.15.255.255 in this case, right? Just 1 IP less. It's easy math at this point. If you make it to here and you didn't mess it up, it's easy mode. But again, don't get too relaxed and don't get cocky, because that's when you make mistakes. So we got 10.0.0.1 to 10.15.255.254. This is 10.16, whoops, 0.1 to 10.31.255.254. And we're done. We've got enough IP addresses to allocate our requirements. Right. Let's do 172 this time. Let's make this a bit different. Let's make it a bit harder. I'm going to treat it as /16 again. Let's do 32 subnets, not 132. We'll make it bigger later. You know what, let's not do 32, that's too even. Let's do 50 subnets. That's a little more different. The numbers changed. The math is still the same, right? Still the same steps. We need our subnet mask initially. So that's /16, so that's 255.255.0.0, right? 2 to the n, how many bits do we borrow to get 50? That's going to be 6. Right? It's going to give us 64 subnets. 1, 2, 3, 4, 5, 6. Now we convert that back up. We get 255.255. Just pause and do it, right? Well, hopefully you already did. It's 252. 128 plus 64 plus 32 plus 16 plus 8 plus 4. It's 252. And our increment this time is going to be 4, right? 1, 2, 4. So now we're going to assign our IPs again. So 172.16.0.0, subnet 0, right? Initial reservation. This one's going to be 172.16.0, not 0. We're incrementing by 4. We're incrementing in this octet, so it's 4.0, right? This one's going to be 172.16.8.0. And now that we have our network IDs, we can figure out our broadcasts. So this is 172.16.3.254. Sorry, 255. Just jumping ahead in my head. This one's going to be 172.16.7.255. We get our first and last usable IP for our range now, right? That's 172.16.0.1 to 172. 16.3.254. 172.16.4.1. Literally the same. Just going to copy paste and change that 3 to a 7. Whoops. And we're done. Yay. All right, one more, and then we're gonna finish up with our slides and call it a day. So let's do a 192.168.0.0/24, and let's do something crazy. Well, not too crazy. In fact, we really kind of boxed ourselves into a corner there. Let's back it off. Let's go 9 subnets. Again, math's going to change, right? Steps are going to remain the same. So that's going to be our mask is what we need initially, right? /24, so that's 255.255.255.0. How many bits do we borrow to get 9? 4, right? Which we actually did this already. 1, 2, 3, 4. Convert that back up. We get 240. And our increment is going to be 16 again, right? So our network ID for subnet 0, that's 192.168.0.0. For subnet 1, we're incrementing by 16. We're incrementing in the 4th octet this time. So it's going to be 192.168.0.16. This one's going to be 192.168.0.32. And so on. Now we figure out our broadcasts. It's 192.168.0.15. And 192.168.0.31. Which makes this 192.168.0.1. 14. And this one's going to be 192.168.0.17 to 30. And again, we're done. Awesome. So, that's an overview of subnetting. Now that's, while it's useful to look at it that way, it's also useful to understand that that's not really the way we do it. Because when we're dividing our addresses up, if you think of your addressing space as like a pizza, right? We're dividing it up into equal size slices. Well, that's not necessarily going to be what you need. You're going to need different size networks to meet different requirements within your organization. You can't just have them all be the same uniform size. That process is what's known as VLSM. I'm not going to show it to you this week. We'll talk about it maybe in the lab and in future lectures. We're definitely going to look at it. I'll show you how to do it, and then we'll do it with a subnetting calculator between now and the end of the semester. But honestly, for your practical, if you can just do equal size subnets, that's good enough for me. So here's what this would look like, right? An organization is going to have an internal network using some kind of private IP addressing. This is how this is implemented. They're going to have a DMZ. This is your public IPv4 addresses, and a router that connects you to the internet. For this, you could use anything, right? You could use a 10, you could use a 192.168. You could do it as a 172.16, depending on the size of your organization, and subnet it down. Anything in that DMZ will be configured with a public IP address. Now, there's also another way to do this. You could actually NAT that, do static NAT for those, and NAT them at the router. And it offers a little bit more security, sort of. Two things we didn't look at. We looked at the number of networks. I'm actually going to get out of here for a second and go into my thing here. We looked at the number of networks in the formula for networks, right? 2 to the n is the number of bits to borrow. But when you're subnetting for hosts, that's not useful. You need to know the formula for hosts. And it's 2 to the n minus 2. Why minus 2? We've got this network ID and this broadcast IP that you have to accommodate for, right? They're going to be included in there, but they're not usable IPs. So that's what you use. 2 to the n minus 2. That's really what this this slide is trying to get across with this crazy binary stuff, right? The remaining bits, that's your number of hosts per subnet. 2 to the n minus 2. Your number of hosts, or number of subnets here, that's your 2 to the n. So here's, we're going to walk through a quick VLSM example. We're going to call it a day. We'll actually give this a better overview later, because I don't want to overload you. We could, if we've got a topology like this, right? We've got 25 hosts here, we've got 20 hosts here, we've got 15 here, and 28 here, and we've also got point-to-point links all across the bottom here. We could do our standard subnetting of, let's look for the biggest number and subnet for that, and that would give us 8 subnets with 30 IPs. But that's what got us into this mess, right? That's a lot of wasted addressing space. You only need 2 hosts down here. Why subnet for 30? That would be crazy. That's what VLSM was intended to do. It avoids wasting addresses. You're subnetting a subnet. That's all you're doing. You're taking that initial step that we did, and you just kind of keep subnetting. So what you end up doing is let's just ignore their graphics and stuff for a second. Okay, we can get to the answer. You take your largest number, or take your networks, and you list them from largest to smallest in that order, right? Top to bottom, an upside down triangle, if you will. You take your largest number of hosts and you subnet for that. You go up to your next boundary. Remember how we always went up to our next network ID? We incremented one more time, even if it didn't exist. And that's your starting point for your next round of subnetting. You subnet that again. You do the same thing and you subnet that again, and you do that same thing and you subnet it again. And you do that all the way down until you're done. And instead of having something like this, where you've got a variety of different hosts with some point-to-points, and you've got /27s across the board with a ton of wasted addresses, you end up with something more like this. So we see we've got /27 here, 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 and here. That part stayed the same. But what didn't stay the same is these are /30s now. We only have 2 IPs because we only need 2 IPs here, right? We have 2 hosts per subnet. It's pretty great. Now, when you're designing networks, you need to come up with a design that's scalable. It's going to grow as the organization grows. You tend to look at you're going to have built-in rules when you're doing this, right? Where you're growing or allocating for, say, 50% growth in each department. So you take your base numbers and you increase them, and also you may have be allocating for an increased number of offices. So like this is gonna grow. Uh, you have to do this in advance because you need to figure out what devices are going to be part of what subnet, what addresses you're going to use, where they're going to go, which ones are going to have public IPs, which ones are going to have private IPs, which ones require DHCP addresses, which means you need to set up a DHCP server. You're going to do this in a project-based course later in the program in a later semester. For your end user devices, you're using DHCP, or if IPv6, you're using Slack, right? DHCP-v6 with Slack, because that's a good thing. But that requires DHCP servers with pools set up. For your servers, those are going to have static addresses, right? And not just servers either. Anything that you want to be able to find on the network, like a network printer, give it a static IP. Internet accessible servers, though, have to have some form of public IP address allocated to them, and usually you do that with NAT, right, where you actually you allocate that IP at the border and you NAT it to something internally in your router. You do one-to-one NAT. Other things to take into consideration are your intermediary devices and your routers, right? Your routers, your access points, they all require IPs. Usually what you do when you're doing this is you'll have like a template for how you're going to do this, a pattern if you will, or I like template better. Your office, one office is going to be configured that way, and then every other office is going to be configured ever so slightly differently, but that exact same subnetting scheme that you've worked out would apply to all. And that is your lecture for this week. Lots of IP addressing and subnetting. So take care, be safe, see you in this week's class. Have a good day. Bye for now.